So 68 here says a pendulum consists of a rod of mass 2 kilograms. So mass 2 whoa. So mass of 2 kilograms and a length of 1 meter with a solid sphere at one end of the mass of 0.3 kilograms and a radius of 20 centimeters. See the following figure. Okay. If the pendulum is released from rest at an angle of 30 degrees, what is the angular velocity at its lower point? So it's released from rest at an angle of 30 degrees, and what's the angular velocity? So I think what I'm going to do is use energy. Yeah, so I would say, well, but here's the thing, and here comes back to this idea of, center of mass, right? Where if I had like a person sitting down like this, their center of mass is right here, right? Where if they stood up, their center of mass is here. But their feet were on the ground the whole time, right? Their feet were on the ground the whole time. So, well, that's a little high of a center of mass, actually. I just wanted to show a shift. Something like it'd be about here. So there's still a change in potential energy, right? Even though their feet were on the ground the whole time. So if we were doing like beginner's physics, that would be like, oh, there's no change in potential energy because whatever. But if we want to really be specific about how the change in energy took place, there is a change in energy. You started down here, the center of mass was here, and now it's here. So the real legit definition of any kind of change in energy of a system is how the center of mass changes. That's often what we look for. And the thing that did work was that the person did work, right? You exerted energy from the food that you used in order to stand up, right? So that's the idea. And it's the same idea that's going to happen here. Most of the time when we look at pendulums, we assume what's called an ideal pendulum. And ideal pendulums, that rod is massless. So we say that rod is massless and it's rigid and that all the mass is concentrated down here. So if it's an ideal pendulum, I could just look at how this mass goes from here to here and use energy, and that's the end of that. However, that's not the case anymore. This is a 2 kilogram rod going against and then there's a ball at the end of it, and the ball only has a mass of 0.3 kilograms. That's a significant amount of mass for this rod. So I cannot just assume that all the mass is, concentrated at the end here. I have to treat this like whatever kind of object it is. So here is definitely the axis. There is the axis. But I'm going to say that the center of mass this would be the center of mass for the rod, but the center of mass with this ball at the end, I'm going to say, it's going to shift a little bit over. Maybe the center of mass is now here. That's the center of mass of the rod here. And so when it reaches here, the center of mass changes here. Not a big difference here, right? Not a big difference in height, but definitely a change in height nonetheless, right? That's going to be my change in height there. So, and then I could use energy, right? I can use energy at the top. At the top here, the energy is going to be, well, gravitational potential energy. So that's my initial moment here. Here's my final moment where it's down here, and here it's going to have rotational kinetic energy. So it's got gravitational potential energy at the beginning, but then at the end, all that turns into rotational kinetic energy, and that's it spinning, where I'm calling this right here my zero mark. So I'm calling this at the bottom my zero mark. I wanted to make sure to establish that as well. And then here's my axis of rotation right here. So if I was going to use energy, then it would be the initial energy is equal to the final energy. My initial energy is gravitational potential energy. My final energy is rotational kinetic energy. And it's rotational kinetic energy because this whole thing, all of this is my system, right? If only this was my object, this was the thing I care about, it would be translational kinetic energy because it'd just be moving like that. But if this whole thing is my object, this is the system or the thing that I care about, then it's rotational kinetic energy because it's spinning about its axis right here. Well, this axis. Anyway, all right. So the height is going to be mgh. So there's h right there. Okay. And then this is for the rotational kinetic energy of this, it's 1/2 I omega squared. And omega is what I'm looking for, right? I'm looking for the angular velocity. So, okay. So, yeah, I'm going to multiply both sides by 2. And then this is the total mass of the system, right? This is the total mass of the system. So, I'll just call that total mass. So the total mass would be 2.3 kilograms, right? Okay, so equals, and so divided by I, and then I take the square root, and there you go. Now I got to find out the moment of inertia, and that's the trickier part here. So the moment of inertia of the system is going to be the moment of inertia of the rod. Well, I got two parts to this. Now there's, so it's the moment of inertia of the rod plus the moment of inertia of the sphere, which I'm going to say, because this is 20 centimeter radius, right? It's not that, like, this mass is definitely significant and this is very small. So I can't just ignore the mass of this rod. And so what I'm doing here is I'm making an approximation. However, this distance is 1 meter. This is 20 centimeters. I'm going to assume this is far enough away that instead of treating this like a sphere, I'm going to treat it like a point mass. But I could treat it like a sphere. I don't think it's going to ruin any kind of error that I have to deal with. So if I want the total moment of inertia of this whole thing, of this whole of this system, it's going to be the moment of inertia of a rod about its end plus the moment of inertia, because this is the rod here is about its end right here, plus the moment of inertia of a point mass, which is this thing here. So the moment of inertia of this system is going to be a rod about its end is 1/3 ml squared. You could look it up, or I'm going to reference you back to my notes, actually, with this part. Because back at notes, I did the moment of inertia of a rod about its end using the parallel axis theorem. And we used the parallel axis theorem and found that it was 1/3 ml squared. So that's what I'll refer to you back in order to find the rod about its end if you wanted to use the parallel axis theorem. Anyway, going back here, so it's ml squared plus the moment of inertia of a point mass. Sorry, this should be the moment of inertia of the rod plus L squared. That's the length of the rod squared. Plus the moment of inertia, so it's mr squared. So the moment of inertia of the point mass, or sorry, the mass of the point mass. So it's mr squared. It's mr squared. So m is the, we'll just say the sphere, because it's the sphere, the mass of the sphere, plus how far away it is from the axis of rotation. This is not the radius of the sphere. This is the radius of the sphere is 20 centimeters. However, it is 1 meter plus that 20 centimeters away, right? So 1 and then 0.2 meters. So r, this distance r from the axis here to here, that would be my r from my r squared. So, and that's going to be 1.2 meters. 1 plus 0.2, so 1.2 meters. So this is 1.2 meters in here. So let's plug this in. I got the moment of inertia for my system is going to be 1/3 times the mass of the rod, which is 2 kilograms. The length of the rod is 1 meter squared, plus the mass of the sphere, which is 0.3 kilograms, times 1.2 squared. Let me just get all that in there. So the system is going to be, oh no, where'd my phone go? Oh, thank goodness, sweet precious phone. So let's see, 2/3, right? That's 1 squared plus 1.2 squared times 0.3. And I get about 1.1 total. So this is, I think I'm getting 1.1. Please check me and let me know if I'm wrong. So 1.1 kilograms meters squared. So there's that, but that's not my answer. I got to plug that all in here. So let's do that. Let's plug all that in there. I'm getting, so I got equals the square root of 2 times the total mass, which is 2.3 times 10 divided by 1.1. And then the height. Ooh, the height is going to be a little bit of an issue too, because the height is, well, let's see. So the length to the center of mass of this thing, well, I could use the center of mass equation, right? So the center of mass, the position of the center of mass of something is going to be equal to the position, so the mass of the sphere times the position of the sphere here, plus the mass of the center of mass of the rod. So the mass of the rod times the position of the center of mass of the rod, divided by the mass of the sphere, or we'll just say divided by the total mass. So let's do this again. So the position of the center of mass is the mass of the sphere is 0.3 kilograms. The position of the sphere we found out was 1.2 meters with respect to the axis right there, plus the mass of the rod, which was 2 kilograms, times the center of mass of the rod. The center of mass of the rod is half a meter, right? That's the center of mass of the rod would be like right there. So that's half a meter. Whoops. Divided by the total mass is 2.3. So the position of the center of mass is 1.2 times 0.3 plus 2 times 0.5, which is just 1. So 1.36 divided by 2.3 is 0.59 meters. And that makes sense because it's not a half a meter, right? A half a meter would be the center of mass of the rod itself, but it's because of this bit of mass, it's shifted a little bit that way. So that makes sense to me at least. Let's get rid of that and simplify things. So now I know I'm going to get rid of this r just to kind of to simplify what I got here. So I got now this distance here is I'll call it a length L, and L equals 0.59 meters. And that means then this length is also L. And so if you know anything about pendulums, I can do a little trick here like this. I think we did this with pendulums with energy, right? And if I called this distance here, if I called this X, right? Let's see, let's push this down a little bit. If I called that distance X, I've made a right triangle for myself here, right? And so X, let's use pink. So X, if I know this angle here is 30 degrees, so sine of my angle is going to be, or no, cosine. So cosine of my angle is going to be X, that's the adjacent part, over the hypotenuse, which is L. So L cosine theta equals X. And then I'm trying to find this height, right? Well, hopefully you can see too, this height plus x is equal to L. So using that off to the side here, the height plus x equals L. And I just found x equals L cosine theta. So this will be h plus L cosine theta equals L. So lastly I get, or not lastly, almost there. This is going to be h equals L minus L cosine theta. I can factor out the L. And I get 1 minus cosine theta. And now I can just plug in everything here to find out what h is. So h is equal to L, which I said was 0.59. 1 minus cosine of 30. So h then has to equal 1 minus cosine 30 times 0.59, about 0.079. I might be rounding way too much, but or not rounding enough, but whatever. 0.0, because it's 0.8 basically, 0.08, but 0.079, let's plug that in there. All right, let's wrap all this up. So times 10 times 2.3 times 2 divided by 1.1, square root of all that, and I get about 1.8. So there we go. So yeah, there you go. So definitely, I mean, this is a tough problem. So using energy is definitely the right idea. But then because this mass is, the mass of the rod is so much bigger or as significant as this much mass, that we can't just ignore the rod and consider this to be an ideal pendulum. So what I did is, well, I used the equation that, basically I start off with energy, potential energy at the top, rotational kinetic energy at the bottom. But then in terms of finding out what h is and I is, that became a little bit of a tricky situation. To find the moment of inertia, we just add up the individual moments of inertia of each part. So I can break it up into parts, like this is a rod. I can find the moment of inertia of a rod, and then I add it to the moment of inertia of this point mass. Again, you could consider it a sphere, the moment of inertia of a sphere, but then you would need to use the parallel axis theorem to show the shift, to show the shift there. And I don't think it's going to be that significant. I think we can just treat it as a point mass. And then we added those together. So remember, r in this case doesn't mean the radius. It means the distance from the axis of rotation. The axis of rotation is here. The distance from the axis of rotation to the point mass's center of mass was 1.2 meters away. That's that distance right here. And then lastly, once we got the moment of inertia, we plugged that in. To get the height, we wanted to find out the center of mass, the distance of the center of mass of the system with respect to our axes. So the center of mass is what I have in that X, that color there. And then the axis was over here. So we found that using center of mass equation, which is on your equation sheet for AP Physics C. And then once we did that, we got 0.59. And then we used a little bit of trigonometry to find out what the height is in terms of things that we knew, like L, that was the position of the center of mass, and then theta, which they gave us is 30, and then found out that the height was this, and then plugged in everything at the end to get omega as 1.8 radians per second.